Welcome to this second set of lecture videos for Physics 4C. In this lecture, we use the wave nature of light that we demonstrated in the last lecture to derive Snell's law, also known as law of refraction. We will first start by introducing the index of refraction as a phenomenological parameter that explains the phenomenon of refraction. We will state Snell's law and also confirm your intuition regarding the outgoing angle of reflection. We will take some time to derive Snell's law from first principles using the wave nature of light. Then we will wrap up this lecture with a couple applications: total internal reflection and a problem-solving example, which also involves refraction and total internal reflection. These laws of refraction and reflection are the basis for the highly practical optical element we will cover next week: lenses and mirrors.
I want to show you how knowing this one expression that comes out of that 1 hour long discussion of where light comes from is helpful in making sense of what you might have had to just memorize in the past. So let me start out with something that I think everyone here has experienced seeing. And I'm saying this because I don't actually have a physical demo. I think I need to get a water tank or fish tank in the future so that I have a demo, but I don't for this semester. So the phenomenon that I'm referring to is what's called refraction of light. So the situation you have to imagine that I actually have demo for that I don't is imagine that I have a tank of water. You are looking at the tank from the side, and it's filled with water. So here's the boundary between air and water. Okay. Below here is water, and above here is air. Now, I do have a laser light, but imagine I'm shining this laser light down into that water. So there's a beam of a ray of light that's coming to here. Oh, sorry. And what happens to this ray of light as it enters this water? Changes direction, right? Most of you somehow know this. I don't know who told you this for the first time or when you might have noticed it for the first time, but most of us know, have an intuition from just living in the world that this changes direction. And if you have thought about this for longer, what you might even figure out is that it changes direction in a way that as it goes into water, it bends towards what we call surface normal, or the perpendicular to this interface. So it'll bend in this direction. As the light comes in, this is how it bends. Right? This is an experimental fact that I think all of us here are familiar with. Right? So here's the question. Why? Why does light bend as it goes in from air to water? Imagine I'm your annoying little sibling who asks why to everything you says.
Because the speed of it changed.
Why?
Because the medium changed.
Okay. So because the medium changed, you are saying that the wave speed is a property of medium, so you can no longer assume that wave speed didn't change. Is that what you're saying? Yeah. So that's one way you can describe it. And in fact, before people knew all of this, people could associate this bending with the change of speed at which light is traveling. You could make that argument. So this is the debate that was going on in the 19th century. They held conferences over this. Is light wave? As people like, I don't actually know their names. I know a guy named Young is one of them. But Newton was actually on the other side. If you've ever heard of Newton's corpuscular theory of light, what Newton thought was light was not wave. It was a stream of particles. particles corpuscular. But whatever that was, both of them, what they could agree on was if light is something that travels at a speed, so in air, speed of light would be something, or I'm going to use the letter C. Letter C is the common letter, lowercase c is the common letter for speed of light. I'm just going to use that. So if the speed of light in air is approximately 3 times 10 to the 8 meters per second, and somehow as it entered the water, the light slowed down, then they could come up with a model that would explain the bending, and we'll talk about that in a little bit. So the one answer to why was, well, speed of light. So this is the speed of light in air or in vacuum. Speed of light in vacuum and air are very similar. You can look at it in your textbook. They are very similar. And what they would say is that speed of light in water was somehow different. If I give a letter V to this, I don't know if I remember the water number off the top of my head. I have to. It's not quite 2 times. Let me just. It's going to be a little bit off, but let's say it's about 2.3 times 10 to the 8 meters per second. So based on, this is what you might call phenomenological description. I don't know if you've heard or seen this word before. Anybody here? So this is, I think, how you spell it. Phenomenological. I think that's the right spelling. I mean, it's coming from the basic root word phenomenon. And when someone says a particular theory is a phenomenological theory, like what do I mean by this word? You could say gas laws that you study in chemistry is a phenomenological laws or phenomenological theory. What do we mean?
First, based on experiment, we see some phenomena, and then we try to come up some theory to explain it.
Yeah, you start out with the experiment, and you come up with some model, any model, to fit to that theory. And this would be a kind of a phenomenological description of refraction of light. You see the light refracting, and you think, hey, if the speed of light was different here, I don't know if it is, but if it were, that would explain it. So based on that, you can sort of assign a phenomenological constant or quantity. And how many here heard the phrase index of refraction? Like that everyone has heard of, right? That's what index of refraction is. It's an experimentally determined quantity. And the way that index of refraction is defined, index of refraction, we usually use the letter n for it. Don't ask me why. It's defined as the speed of light in vacuum, c, divided by speed of light in whatever medium that is. So these two quantities are the ones that go together. This v is some kind of property of the medium, speed of light in the medium. And this index of refraction is essentially a way of expressing the exact same information. You could say, based on what we wrote down here, that speed of light in a medium is its speed of light in vacuum divided by index of refraction. So all of this is just a phenomenological description, as in we have no way of describing, not no way. we don't have, I guess the opposite to phenomenological is the counterpart to phenomenological theory is something that you might describe as first principles. In fact, almost everything you did in physics 4A is that. As in, you start out with Newton's law, that's your basic fundamental law, and you build everything on that without introducing any more assumptions. A lot of mechanics is that, except when you start measuring friction coefficient and things like that, then it's a phenomenological again. This is what a lot of engineers do. This is what a lot of theoretical physicists like to do. And what we can say is that based on what we covered in the last hour, we can actually give a little bit of flair of how to describe this different speed of light in a medium in terms of something that's more fundamental. As in, imagine, as I said, imagine you have an annoying younger sibling who keeps asking you why. So you tell your younger sibling that light bends as it enters a different medium because the speed of light is different there. In fact, I can even tell you that this is how they are different. This is the speed of light in the medium, c divided by n. Anybody here know what the value of n is for water? Once you know, it's an easy number to memorize. N of water is approximately 1.33. You can put one more 3 there, but that's already 3 significant figures. So after you've given all that, imagine that your younger sibling once again asks you, why? Why is the index of refraction of water 1.33? This is where we can look at this to have a bit of a more conceptual basis. That's not simply saying this is true because we know it to be true. Why is it true? Because it's true. Like you're not explaining anything. You're just insisting that in science, that's sometimes how it works. You do the experiment, so you know what the correct result is, even when you don't understand why. But with this theory, here's how we can describe it. When I say the names of these constants, I never say permittivity and permeability. I always say permittivity of free space, permeability of free space. Why? Why do I keep adding free space? Do I like free stuff that much? I mean, I do, but what does free space mean? Yeah, vacuum. These are constants that are specifically associated with vacuum. This is the electric constant this is the dielectric constant of vacuum. This is the magnetic constant of vacuum. Water is a dielectric. So water has a different dielectric constant than air does. So what you can do is you can build an expression that's similar to this, but for light in water. So you could say this speed of light in some material is equal to 1 over square root of whatever that dielectric constant is and whatever that magnetic constant for the material is. It's often equal to mu naught. It's usually the electric constant that changes a lot. So this is the more fundamental connection. I mean, not that your annoying younger sibling would understand it, but you can, once you make this connection, then you can actually design an experiment that would confirm for you that that is why the speed of light in water is different. You can maybe do an electric experiment, and you will see that the amount to the dielectric constant is different by actually matches it. In practice, it gets a little bit complicated because this is a function of frequency. Light is a very high frequency electromagnetic wave. And when you do electrostatic experiment, the result is, that's a complication. You will deal with it when you're actually doing physics research. But this is at least the starting point. You can connect to something that you knew almost intuitively, something that you just took on faith, to something that's more theoretically grounded. We are still on refraction. One more thing to cover. Anybody here know how what law? If someone remembers from maybe high school physics, tell me the name of the law that tells you how much this bends.
It equals sine something, right?
It involves sine. I'm looking for a name. Here's the reason I'm looking for a name. If you know a name, you can Google it. That's why names are useful. Anybody remember the name? It's a kind of funny sounding name. Sounds like a bug. Well, maybe it's not a bug. Is it invertebrate? Who here knows a lot about snails? So it's not Snell's law. Yes? Yeah, Snell's law. Let me spell it. So once again, Snell's law, you could look at it as a phenomenological law, as in people, people found that this is somehow just worked. But we can actually justify Snell's law based on our understanding of light as a wave. So this is what Snell's law says. Snell, this is how you spell Snell, not Snell. So Snell's law says, so it involves the index of refraction. And this is a good point for me to tell you how we measure angles in optics. It's kind of I think it's a bit of an unintuitive way to do it, but that's how people do it. And I think in the long term, this is the more sound theoretically way to do it. So this is the picture of a refraction, right? Let's say I want to describe the angle at which the light is coming in. I see many different angles. I see two in particular. I see this angle here, angle between the surface and the ray. Call that phi. And I see one more angle, if you look hard enough. Angle between the ray and this imaginary line. Let me call that theta. Which angle, phi or theta, do you think we'll use to describe Snell's law? Theta? Anybody think we should use phi? So why theta? I mean, this is such an unintuitive angle. Like even to see it, you have to draw this imaginary line. Right? What's so special about this imaginary line? It's the normal. What's special about normal to a, so if this is surface, what's special about the normal to the surface? Well, sure, what's special about it being perpendicular? It's at 90 degrees. That makes it something, so let's see. This is something we were dealing with in physics 4B. Let's say you have a plane and you want to describe the plane, direction of the plane. If you wanted to associate a single vector to describe the direction of this plane, can you do it with any vector that's within the plane? No, right? So if you want to use a single vector to define the direction of the plane, that's where you use the normal. That's why this imaginary line that I drew, it's actually pretty special. When you think of this as a three-dimensional thing, there's only one line I can associate with this entire plane. So the angle between this normal or perpendicular and the ray, that's the special angle. That's the angle we are going to use to describe the direction in which this is coming in. Yeah? So that's one kind of an unusual, unintuitive thing that I have to go over. Because a lot of people, if you just got thrown into this without this auxiliary figure, you would guess that you measure this angle, and no. You draw this auxiliary figure, and you measure this angle. That's what you need to do. So I can label theta 1, and let me actually use theta naught and theta 1. So I'm using the subscripts to sort of separate out, this is the medium 1, and this is medium 0, or vacuum. And this is what Snell's law says. We do these descriptions of angle, we do this index of refraction. So I mean, if I'm being completely thorough, index of refraction of air is approximately equal to 1. It's like within a factor of, within 1 part in 1,000, it's equal to 1. So Snell's law says that this combination of quantities is constant. Index of refraction times sine of theta naught. that this particular combination of quantities that only involve quantities in one medium is constant as light goes through a boundary. That means the way it's usually given is this is equal to n1 times sine of theta 1. But the reason I wanted to highlight this first was imagine you had a third medium, and here's medium 2, and then it refracts again. Then you can actually simply chain them together. You can say, and this is equal to n2 sine theta 2. So this is Snell's law. You might have seen it in high school physics. Well, I guess if you had an annoying sibling who kept asking you why, at this point you don't really know why. Like, what do you mean why? That was in the textbook. And in a little bit, I actually want to look at this refraction picture with a picture of the wave in mind, and actually derive that it has to work out this way for things to make sense. If I have this light that's going into beaker, oh wow, you can actually see it. Let me have the water calm down first. So something else happens other than the refraction, which is the light going into beaker. What else happens? Yeah, sorry, water's a little bit too crazy, but you see the reflection, right? Yeah. So on a smooth surface or smooth-ish surface, as you get the refraction, you will also get reflection. You'll get a reflected, what color haven't I used? You'll get a reflected ray that goes roughly in this direction. So I can also describe the angle for this reflected ray. I guess I'll describe the same way I've been describing. This angle here, angle between the light ray and the surface normal. And this reflected ray, theta r. Does anyone here know intuitively how this relates to other things? Yeah, this angle of reflection is equal to angle of incidence, right? That, like, you know, when you hear that, that sounds familiar, right? As if you've heard this somewhere, or it just makes intuitive sense that this theta naught is equal to theta r. Like, it sounds true. It's like somebody telling you 1 plus 1 is equal to 2, or 1 plus 4 is equal to 5, and like you don't question it. If someone asks you why is this true, then that's where most people would sort of be at loss for words. It's like, why should it be that whatever angle it came in should be the angle that it went out in?
Conservation of momentum. I don't know.
Why should it be conserved? I mean, it's interacting with the medium. The medium is very heavy. It can carry away whatever. Because you're thinking of a ball bouncing, right? But when a ball bounces, momentum isn't actually conserved, right? So I'm actually not going to do this part because, I don't know, too long. I like the other one better. But I want to point you to the part of the textbook that does cover it. The part of the textbook that does cover it is I'm just not going to be able to say the name right. Huygens principle. I don't know how to say the name right. So this is the section of your textbook that describes a principle that you used for describing waves, wavelets, and how you deal with that. And this principle can be used to describe, for example, propagation of a plane wave, and sort of where the law of reflection comes from. And all this picture is very complicated, which is why I don't really want to get into it. Read the textbook, however much sense it makes to you is great. What I want to spend a little bit of time with is what's in this picture. What's in this picture? And I have to introduce a couple concepts before I can get to this. So let me first describe what's called, what is termed wavefront. Have people heard the word wavefront before? Yes, no? Let me show you the graphical representation of a wavefront. So I have this simulation of a wave. Oops. It's a simulation, but this is a reminder of something that you have seen many times before. Water waves. Imagine you have a tub of water, you keep dropping water, you see water waves forming across it, right? And maybe, I don't know if you look at it from top, it'll look like this. But what you definitely can say is that if you turn it around, then what that wave is, it's a variation of the water level. There's some particular level that the water would be at if there was no drop at all, right? And as the water drops, disturbs the water, it causes this ripple. Okay? So what I want to call wavefront, it's very similar to what you see here in the top view. So in the top view, you are not really seeing something that's oscillating up and down, right? But what they are using, the graphical tool that they're using to illustrate that is they have some point that they are marking as a dark spot, right? And it almost doesn't matter if this dark spot is a high point in the wave or a low point in the wave. What matters? It's that it's a point, a consistent point in the wave. So if I switch back to the other view where the wavy nature is more clearer, I would be looking at, let's say, this point of the wave. And as I track this one particular point of the wave that has the same phase, that's the same portion of the cycle of the periodic wave, that's what we call wavefront. So it's a terminology, it's a way of graphically illustrating waves so that we don't need a fancy simulation to illustrate wave when we want to. And that's what you see in this diagram here. This is, so these lines are representing a wavefront. As in, imagine you have an electromagnetic wave that's oscillating, and this is a particular point on that electromagnetic wave oscillation. Maybe this is the point where electric field was pointing most out of the board. And then it'll cycle, it'll sort of get smaller, point into the board, and then get smaller again. And when it points out of the board again, this is the next wavefront. So from wavefront to wavefront, that would be one wavelength. Yeah. So that's the graphical tool. And I guess, 15 minutes. Oh, that's more than I thought. I guess since I have this picture from the textbook, might as well use it. So this is an illustration of that. Let's take a little bit of time just dissecting this picture. Some portion of it you are already, you can guess what it is. You can guess that this is the ray of light, and this is the ray of light bending as it goes into water, right? These wavefronts, they take a little bit of more explanation. So this wavefront picture is added to imagine you have not a very narrow ray of light, but imagine this is more like a flashlight that's covering a wide area that's just coming in. So I could take this picture and just draw it parallel side to side. So this is all the bunch of rays that are in that wide beam. And I can illustrate that beam with its propagation direction, or I can illustrate that with this wavefront. If we are dealing with a plane wave, as in wave as it's moving, the only direction in which electric field is changing is the direction it's moving in. If you go in any other direction, the electric field remains the same. Then this is the set of points in space where at a particular moment in time, electric fields have the same magnitude and direction. Yeah? And at that same moment in time, you can actually find another set of points that have the same magnitude and direction of electric field as here. That's the next wavefront. And we are dealing with the periodic waves here. That's why these same values of electric field occur over here. And if you go same spacing over, you would see the same values of electric field occur again. And so on, and so on, and so on. Right? So this spacing between these two, that's what we call wavelength. So it's an illustration of wavelength in a way that maybe you haven't seen before. I don't think I covered this when we do physics 4A. But this makes sense in terms of diagram? Yes? Now, let's say this is a light of a particular frequency. So it has some amount of fixed frequency. So it's a light with, let's say, frequency f. Then we know an expression for what this wavelength is, right? For a periodic traveling or periodic wave, wave speed c is equal to wavelength times frequency. So if you solve it for wavelength, that ought to be equal to wave speed, c, speed of light in vacuum or air, divided by the frequency. That's the wavelength here. Right? As this light enters a different medium, what changes? Does the frequency change? No. The assumption, yeah. So in most cases involving optics, the assumption which is true most of the time is that frequency is determined at the source. If I have some charge that's oscillating at 1 hertz, and that's producing an electromagnetic wave, then as this light goes through many other places, it's going to remain oscillating at 1 hertz. One exception that will come later is something called the Doppler effect, but let's not worry about it now. So the frequency at the source determines what the frequency will be here also. So as you look at this expression, if we are saying frequency of light doesn't change as it enters water, can the wavelength stay the same? No, right? Because the wave speed is decreasing. So if frequency is same, then the wavelength must be smaller. And that's what this picture is saying. Plus one additional condition that I hope you will find intuitively true in a rigorous way, not just I know it to be true. And that's this. So imagine that we are obstinate and we insist that this light is going to keep going straight, not bend, right? Then this is the difficulty that you see as you kind of draw what the light, how the light looks like. So the ray, whether you draw it straight or bent, doesn't look like anything's wrong yet. So the inconsistency comes in when you draw the wavefront. So I have these wavefronts in air, right? Let me draw just one more here. So these are the wavefronts in air. In water, if I'm going to draw wavefronts, this is how it's going to look with this purple line here. So the wavefront will still be perpendicular to the propagation direction. So it goes in this direction. Now, if I connect it this way, that's wrong, because then I'm saying that the wavelength here is same as the wavelength here. We just talked over that. That's not the case. So if I draw it the other way with a shorter wavelength, then this is what I get. And this is wrong for a different reason. What you are seeing is a discontinuity here, right? What's wrong with the wavefront not being continuous? What's wrong with the wavefront just jumping from here to here as you cross the boundary?
all things we get is a continuum function.
Yeah, I think that's a good starting point. Whenever in physics, whenever you see something that's discontinuous, the first thing you should be is suspicious. Sometimes that can happen. In fact, in quantum mechanics, sometimes you'll see when something is discontinuous. But anything that's discontinuous, as a matter of presumption, it's unnatural. You don't usually see that in physics. Here, the way you might justify this, based on knowing that these are based on electric fields, is discontinuity in wavefront represents discontinuity in electric field. The value and direction of electric field here is in some direction. And as you cross this boundary, the electric field is suddenly changing. And if you have done application of Gauss's law in an upper division setting, you would notice that that corresponds to having some charge density here. And I did not want to deal with the charge density here. I'm not dealing with the static electricity. So this is a rule that we use in optics. The wavefront has to be continuous as you go across the boundary. That's the rule. And it's a rule that you can justify from basic electrostatics or basic electromagnetism. So these are the two conditions we have to meet simultaneously. Simultaneously, we have to be able to say that we have to be able to set the wavelength is shorter here. And where the wavefront join at the surface, they join. They are not discontinuous. And the picture that you draw on here is the only way to meet both the requirements simultaneously. Because if you say, as the light comes in, it bends, now you can draw this wavefront with a visibly shorter wavelength, but because it's at a shallower angle, by the time they come to join here, they join in a way that they are not discontinuous. Okay? So now that you have this picture, now you can figure out Snell's law, or at least you're supposed to be able to figure out Snell's law. Let me see if I can. Let's see. I think these two labels are supposed to be useful. So t is the period, v times t, that gives you the wavelength. All right. I feel like what I should use is, sorry, I didn't work this out beforehand. So this is the segment that both the sides share, right? So I think I need to be able to set this segment represented using the quantities here is equal to this segment represented using the quantities here. So let's try that. And I do know the quantities that I'm eventually going to use. So this is the angle theta 1. This is the angle, oh wait, they already labeled it. Why is it so far? Well, this is angle theta 2. I'll use this. All right. So this is, you use a geometry more in this class in any of the other physics classes. Geometric optics. We call it geometric optics for a reason. You're going to be using geometry more. So if you go back to doing geometry, by the way, I find it difficult to teach geometry. There's no systematic way to do it. You just keep drawing auxiliary figures. You keep labeling things until you figure something out. And I think that's the only way I've been able to approach geometry, and that's what I recommend. So I'm just going to keep labeling things until things start to make some sense. Let's see. So what I do know is that this should be perpendicular because it's a wave propagation direction and the wavefront. They're always drawn perpendicular. That means this angle here is 90 degrees minus theta 2, right? I know this is also perpendicular. So that must mean this is theta 2. Yeah? Okay, I got theta 2 in the triangle that I kind of wanted it to be at. Good? And I need to get theta 1 where I want it to be at. I guess I can go through something similar. Let me do it in different colors so that it's less confusing. This angle is 90 degrees minus theta 1, right? Oh, I think this is a right triangle. This is a right triangle, as in this is 90 degrees. So this plus that is 90 degrees, meaning this angle here is theta 1. Everyone good? Okay, I think I actually have everything now. So for this right triangle here, I know this leg, that's V1t. So, and I know one angle here, so I can express the hypotenuse. The hypotenuse here is, so this is the opposite side over hypotenuse. So let me write it down that way. So opposite side, V1t, over the hypotenuse, let me call it capital H, is equal to sine of theta 1. Let me write down a similar expression for the other right triangle, for this right triangle here. So, wait, is this one adjacent? I don't like that. No. So the side that I know is this side. It's the opposite to theta 2. Good? So I can say opposite side, V2 over T, V2 times T over the same hypotenuse, so I'm using the same letter H, is equal to sine of theta 2. And this is how you derive Snell's law. There's one other way to do it, but well, this is one way to do it. So each of these expressions, we are going to solve it for H, the hypotenuse. So this becomes V1t over sine theta 1 is the hypotenuse. And this expression becomes the hypotenuse is equal to V2t over sine theta 2. So we just say these two are equal to each other and skip the hypotenuse. Once you do that, then you can get rid of a lot of arbitrary quantities, like the time period t. Because in the end, we want an expression that doesn't depend on frequency or wavelength. So far, this is what you have. V1 over sine theta 1 is equal to V2 over sine theta 2. Then you recall back to the definition of index of refraction. Because when you're talking about the actual speed of light, it's such a large quantity that you don't ever really want to be dealing with it all the time. So using this, let me say V1 is equal to C over N1. So I'm going to do the substitution for both of them. So V1 is going to be C over N1. And V2 is going to become C over N2. So the numerators cancel out. It's 1 over this is equal to 1 over that. You could just say the denominators are equal to each other. And you get N1 sine theta 1 is equal to N2 sine theta 2. So that's one way to explain or derive Snell's law. So rather than leaving this as a phenomenological law that it's just true, you can actually say, based on enforcing these conditions involving wave propagation that we were talking about, Snell's law is the only way to have propagation of light be consistent with wave propagation. So this is the situation I want you to think of. I guess if you want a more kind of closer to real life example, then it's this one that you want to think of. This is one of the problems in your problem set. Let me open just the image. So this is a description of some setup where you have a pool. There's a calm pool surface. So this is illustrating refraction. So there's a guy here who's out in air. The line of sight from him. So you kind of have to imagine the way we draw line of sight. Often it'll look like the light is coming out of the eye and then into water. Unless you are Superman, it doesn't work that way. It works the other way. Light is originating from here, coming up, refracting here, and then entering your eye. The good thing is with these rays that we draw, the direction actually doesn't matter. Whether light rays are going one way or the other, it bends the same way, traces the same path. So you can kind of pretend that there's a ray coming out of the guy's eye, entering water, and then bending down that way. So that's the refraction, right? Now, this is what I want you to imagine. How do you think this refraction will change as this angle becomes larger and larger? That is larger measured from normal. What's the largest this angle can get? 90 degrees, right? The almost grazing angle. So if we have this as the boundary between mediums 1 and 2, then what you can imagine is, so you could have something that's drawn like this, kind of pretty normal, general kind of description. But another thing you can have is you can have, let's say, this is where it's going to cross, and the light can be coming so close to the surface that this angle here is essentially 90 degrees. Now, how do you think this will refract? How many think it will go straight, in a straight line, so that this is also 90 degrees? You think that might happen? Okay, I guess yeah, I don't have a lot of good optics demos that I can show on the board. Sorry, I wish I did. You will see some of them in the lab next week. So this is where this is one of the goals in physics. In many areas that we deal with in physics, you won't have good intuition for. That was true in physics 4A and 4B. Even when you're doing mechanics, sometimes the intuition you have is not the correct intuition. In physics 4C, it's especially even more true that you simply do not have the intuition. For optics, maybe some of you do. When we get to special relativity and quantum mechanics, we have a saying: nobody is born with the intuition for special relativity. Nobody is born with the intuition for quantum mechanics. So one of the goals in physics is that you start to build that intuition. And the number one tool you have for that is the mathematical relationships that we introduce. So here, we're going to start out with that. What we can rely on is that Snell's law is true. We even derived it last time looking at the wavefronts. So we start out with that. The n1 times sine theta 1 is equal to n2 times sine theta 2. Let me make this a little bit more realistic and give you actual numbers. Let's say this is air and this is water. Same as what's in that picture over there. So anybody here remember the index of refraction of air? Approximately? Approximately 1? Yeah. Close enough to 1 that we are going to say it's 1. I think I did mention water last time. Anybody remember? 1.33. Yeah, 1.33. So index of refraction in water is 1.33. All right, so this is an expression containing four different symbols. And I know 2 of them. Do I know value of any of the symbols? Which one? Theta 1. Yeah, we know theta 1, 90 degrees. So what's the left-hand side, actually? Just the 1, right? Okay, that's promising. Now, I think this is a point where you have filled in enough of the blanks. Now you can intuitively guess some of the features of theta 2. Will theta 2, the outgoing angle, so this was theta 1. will my theta 2 be 90 degrees? No, right? This is bigger than 1, which means this has to be smaller than 1 so that this can, so that the product can equal 1. Right? And I guess, let me just do, so if you work out the expression algebraically, what that would be is theta 2 is, let me do this in my head, arc sine of n1 sine theta 1 over n2. Did I do the algebra correctly? Yes? Yes. Okay, let me plug in those numbers so that we have something concrete. So we are looking for arc sine of, well, I guess 1 divided by 1.33. I wish I could do that in my head, but I can't. Radians, okay, there it is, degrees. 48, wow, that is a lot smaller than I would have guessed. So if I'm trying to draw this to scale, it would look something like this. This is the refracted ray going out at an angle of something like 49 degrees or so. Good? Yeah, and if you didn't have this intuition before, then now hopefully you do. This fits with a more conceptual, descriptive, description of refraction that you may have heard. When a light ray goes from material of a smaller index of refraction to the larger index of refraction, anybody here have heard the phrase that follows in conceptual physics? The light ray bends towards the normal. And that's what it does here. And the amount it bends, if you go through this numerically, you will see how much it deflects, it actually gets bigger as this angle is bigger. So when it's at 90 degrees, then it doesn't bend at all. Or sorry, when it's at 0 degrees, then it comes out at 0 degrees. As it goes from 0 to 90 degrees, the difference, the amount you see here as a proportion of the angle does get larger. So right, that's it. Nothing all that surprising. The surprising feature that I want you to bring up, and this is the feature that's called total internal reflection. It comes in from a slight modification of this picture. So this is what you have seen. When you are coming straight down, so if you had a ray of light coming straight down, then it would have, so theta 1 is 0, then theta 2 would be 0, it would have gone out like this, right? And you can imagine, as this sweeps across, this will sweep across this way. When would this ray, outgoing ray, ever be in this region? Never, right? Which means, so this is what I started out this section with, that when you have a ray of light, the direction doesn't matter. You could actually go the other way, and it would trace out the same path. Now, what we are seeing is that if we are imagining the source of light starting from this side of the boundary, then here's this region that the light rays will never reach. Now imagine that you have some source of light here. I don't know. This is my light bulb. Imagine you have a source of light here. And let's say there's a light ray that's going towards this point. So this is my light ray that's going towards that point. If there is any refracted ray, how should it refract? So it's going from the higher index of refraction to smaller index of refraction, right? So you would expect it to bend away from the surface normal. But here's the thing. This ray, when you reverse the direction of this ray, is supposed to go like this. So this ray should be even larger angle than that. Is that possible? No, it's not possible. In fact, when you plug in the numbers into Snell's law and try to do the calculation, you will see. Depending on your calculator, if you solve for theta 1, either you get out of domain error or you get a complex number, depending on your calculator. So this is the condition where total internal reflection happens. So if the light is coming from this range, there's no, well, it cannot refract. There's no way to get a ray on this side that's consistent with Snell's law. So what happens is there's still energy in this ray of light. It all has to go somewhere. And what it does is instead of refracting, so refraction doesn't happen at all, it all reflects. This is what's referred to as total internal reflection. And when you look at very high quality optical instruments, I guess they use this in binoculars. Even the best mirrors, like those metal mirrors, the highest reflection you can get, well, metal mirrors actually are not that good. They have 95% reflection. If you want 100% loss-free reflection, this total internal reflection is one of the ways. If you have this very high quality boundary, then so there's no like energy loss with the interaction that's going on at the boundary, then this beam is prohibited prohibited from refracting through to this side. So all of this incident energy has to reflect and come out on the same side. So, so this expression that I wrote down, I can get the critical angle for total internal reflection from here. So let's say I wanted the theta critical angle. So this would be the smallest theta at which total internal reflection happens. Any theta larger than that will always lead to total internal reflection. Any theta smaller than will have some refraction. So this was just came from Snell's law. It's just Snell's law rewritten. What condition would you impose on this to say this is the critical angle? This is the smallest angle at which total internal reflection will happen. So one small condition. Sorry, somebody was saying something, but I couldn't see. Smaller or, you said the 90 degrees, right? Which angle were you referring to? Theta 1 or theta 2? Theta 2, the angle on this outgoing side? Yeah, theta, the angle on the incoming side, right? So, if you have an optical arrangement that would lead to theta 1 being anything smaller than 90, would it result in total internal reflection? No, 90 degrees is that critical angle for theta 1. So for a critical angle for theta 2, I'm going to set my theta 1 equal to 90. So 90 degrees. So sine of theta 1 will be 1. So this critical angle, it should be equal to arc sine of n1 over n2. So if you have an incident angle, that's so this would be my incident angle. If you have an incident angle that's larger than this critical angle, that's what results in total internal reflection. And so this is something I'm hoping that you will eventually learn to do on your own. If you look at this expression for a little bit, for a right length of time, I hope you will notice one condition you can say is necessary for total internal reflection to happen. Because it's not true that you can always get total internal reflection. Like, I don't know, last time I had so I have this beaker of water. If I have this beaker of water and I shine light from outside into this water, no matter what I do with it, so you can see how much is reflecting there, right? And no matter what I do, you will never get total internal reflection here. So there's some particular condition that I need to be able to meet that with this setup, me shining laser light into beaker, I will never get. And if you stare at this for a while, you can figure out what that condition is. Any guesses?
N1 has to be smaller than N2.
Yeah, why does the N1 have to be smaller than N2? Javier, you were answering.
Domain of arc sign.
Yeah, so you look at the arc sign. So this is what physicist or engineer, someone who's trained in quantitative science does. Arc sign is in your formula, and this function has some requirements. It doesn't have a domain of all real numbers, unless you extend it to complex domain. So it only can produce a reasonable answer from -1 to 1. So if somehow something causes your input to go outside of that range, then that causes it to behave in a way that you weren't expecting. So yeah, here the condition is that n1 must be smaller than n2. That means here, n2 was the incident side. So the light has to be coming in from the side that has higher index of refraction. So for me to get total internal reflection here, I'll have to put this laser into water and shine in from water, but this isn't waterproof, so I'm not going to do that. So there are other arrangements that you can use to get total internal reflection with the light starting from air. One of those you will see in your homework. Let me see if I can find it without wasting too much time. I feel like it's one of these. Okay, this one. So this is this shows one arrangement where you can get the total internal reflection. So this is a prism. So when the light comes in normally here, it doesn't bend at all. Now on this surface, now it's coming in from the glass side, trying to go into air. So you can have total internal reflection on this surface. So, but that's an important feature in total internal reflection, and it's built right into this formula. And when you think about it for a while, this formula itself, it's like, I never actually memorized this because you can get it directly from Snell's law. If you just remember that for the critical angle, what you are thinking is you want theta 1 to be 90 degrees.
Problem solving with an example. This is an example from your pre-lab 1. And I saw in your answers quite a few people struggle with this question. This is why I thought I would use this as an example. And the question asks you to express the index of refraction of the prism as a function of theta z, which is the only parameter you can measure in lab. So it's not an easy question, and it takes a detailed step-by-step problem solving, which is why I thought this would make a good example. When you get a question like this, the very first thing you should do is not dive straight into the problem. The very first thing you should do is first to look at the given situation and see if the question that it's asking makes sense. Specifically, does it look like you have enough information to determine the answer uniquely? So if you read the description of this diagram, this theta z is set in a very specific way. This is the angle of incidence for which the eventual outgoing ray here is at critical angle, so that this theta 4 is at 90 degrees. And it's worth a minute or so just staring at it, thinking to yourself, if n2 were a specific value, if all the way in which this will happen is all determined, or if there are some alternate ways it can happen. So now once you convince yourself that all the necessary information is there, that's when you should start compiling this information, mostly in the mathematical language. I like thinking sequentially. So let's just start from the beginning and let's just step through this interaction step by step and compile all the information as we go. The beam comes in at angle theta z and it refracts through this surface here. That sounds like a piece of information I should write down. So that refraction is governed by law of refraction, or Snell's law, which is represented by this equation I wrote down. And for the time being, I'm not going to worry myself with the fact that I don't know theta z and I don't know theta 2. Alright, moving on. As the light continues, it tries to refract through this surface again. So we'll write down another law of refraction. And this is where it's good for me to remember that we are looking for critical angle condition here. So theta 4 is 90 degrees and sine of theta 4 is actually 1. And in writing down this equation, we introduced one more unknown, theta 3. So that's the end of the interaction. So if an easy question, we would have all the information necessary at this point. Here's how you should check if you have all the necessary information. You count your number of equations and your number of unknowns. Here I count 1, 2 equations, and I counted the 3 unknowns so far. Oh, let me change them around a little bit. I guess I'm assuming I will know theta g because I'll measure it, but I don't know n2. Still 3 unknowns. Equations represent information. It's a relationship that'll help you figure out unknown quantities in terms of known quantities. So what this is showing is that I don't have enough information. Hopefully you remember from algebra, to solve for 3 unknowns, you need an independent system of 3 equations. So there's an equation missing here that I'm on the search for. And hopefully after a little bit of staring, you realize that it would be good to be able to relate theta 2 and theta 3. Because here it looks like they should be related geometrically. This is where auxiliary figures are helpful. Let me zoom in and draw a few auxiliary figures here. Alright, it looks like a theta 2 and theta 3 are part of this triangle here, whose 2 other sides I have drawn. So there's an angle here that we need to figure out. And let me extend this auxiliary figure a little bit here. Then you can see that this line here is parallel to this line here. This is 45 degrees. Which means this tiny triangle here is a 90, 45, 45 triangle. So that gives this angle here as 135 degrees. Alright, I think I have enough information to write down a relationship relating theta 2 and theta 3. They are internal angles of a triangle and we just figured out the third angle. Let me zoom back out. So my third and last equation is that sum of these 3 internal angles of triangle are equal to 180 degrees. This third equation introduced no new unknowns, so I still have 3 unknowns, but now I have 3 equations, so now I know I can solve it. And this is the practice that I want you to start getting into. When you're solving mathematical problems for classes like Physics 4C, where you are going to see challenging questions, I want you to treat all questions as a 2-step process. The first step is information gathering step. This is where you have to recall laws of physics, mathematical relationships that you might know, maybe some theorems. That's the very first step, gathering all the necessary information and being able to recognize when you have enough information. And the second step is, I like to call it just algebra. Now that doesn't mean it's easy, but separating it into these 2 steps allows you to figure out what you need to work on more. Do you need to study physics more so that you have these things like Snell's law at your fingertips to use them when you need them? Or do you need more algebra practice? Because what I see is that a lot of students actually could use more algebra and trigonometry practice. So now that we compiled all the information, the rest of this question is really that, algebra and trigonometry practice. So let me go through that. Now, I want to be deliberate here. What I want in the very end is n2. These theta 2 and theta 3 are intermediate unknowns that I'm not really interested in. So my goal is going to be to eliminate them. And there are different strategies for eliminating unknowns. The one that I like, because it works every time, sometimes it can be tedious, but it works every time, is substitution. So these are the steps in substitution. You solve one of the equations for the unknown that you are trying to eliminate. So let me solve equation 3 for theta 3. Now I can plug this into everywhere where I see theta 3 to get rid of theta 3. So I see theta 3 only in equation 2. So let me plug that in there and let's see what we get. Now, these are the two equations you have left at this point. N1, which we haven't touched, and N2, which looks like this. Now, my goal here would be solve one of those two equations for theta 2 and plug it into the other equation, hoping to get one equation in terms of only N2. But the challenge here is that theta 2 is inside all these special functions. So it looks like I need to use a little bit of trigonometry. I hope all of you remember the angle addition formula. It's the one trig identity that I would highly recommend that you memorize. Just because one, how useful it is, and two, how difficult it is to derive if you don't know it. So this is the sine angle addition formula. That is, sine of alpha plus minus beta is equal to sine of alpha times cosine of beta plus minus times sine of beta cosine of alpha. So let me apply to that the underlined expression for sine of 45 degrees minus theta 2 and see what we get. We can use the fact that sine of 45 degrees and cosine of 45 degrees, they are both 1 over square root of 2 to simplify this a little bit. Let me write down the simplified version. Alright, here's a little bit of difficulty. I still have two equations, n2 unknowns, n2 and theta 2. But I have two different expressions involving theta 2. So there's a sine of theta 2 and cosine of theta 2. There are different ways to approach it. This is the one that I have learned, is to express in terms of new variable. Let's call it x. X is equal to sine of theta 2. Alright, then I remember my Pythagorean theorem, which says sine squared theta plus cosine squared theta is equal to 1. I can solve that for cosine to get this. Cosine theta 2 is square root of 1 minus sine squared theta 2, or x squared. So now you see that it's going to be a little bit complicated algebraically. We are going to have to use quadratic formula. So plugging these in, you get square root of 1 minus x squared minus x is equal to n1 over n2 times the square root of 2. So this is my newest version of equation 2. And let me write down the newest version of equation 1. That is n1 times sine of theta g is equal to n2 times x. So you have these two equations, two unknowns, x and n2, and you should be able to solve for it. The next step to do might be to solve equation 1 in terms of x. Then you can plug it into the x's you see here, and then you solve for n2. Let me leave that as an algebra exercise for you in the interest of keeping this video short. I'll just write down the final answer for n2. So when you go through all the solution steps, n2 is equal to n1 times square root of sine squared theta g plus parenthesis sine of theta g plus square root of 2 squared. Depending on the exact algebra steps you go through, there are a couple different forms that this final answer can take. So verify if your answer is equal to this by checking it numerically. So that's it for this video. Let me just leave you with this note. Mathematical problem solving takes a lot of practice to get good at it. But as a starting place, I want you to get into practice of separating the steps into two distinct steps. This is the very first step, getting all the necessary information. This is really testing, do you know physics? And all this stuff here, which might take you a lot longer, is math. And your entire career as a scientist and engineer will be a long process of getting better at algebra. So until next time, bye.